All right, so this is part 2 of Unit 2, and we are going to be looking at polynomials, and eventually we're going to get to, by the end of this video, graphing polynomial functions. And first, before we get to graphing, though, we want to kind of have a definition of what is a polynomial. So we're going to do some comparisons between functions that are polynomials and functions that are not. This right here, this long, what looks like a formula, but is really actually a definition, is what a general polynomial is. So the largest term here, this would be the degree of the polynomial, degree n. That's the largest exponent. And then this number in front of it would be called the leading coefficient. And then we have the next highest exponent, the next highest exponent, all the way down to just the linear factor, and then the constant on the end. So this would be the constant on the end here. And so this is just a general polynomial. It's not a formula we're plugging things into. Now here are some examples of polynomial functions. If I just have x to the negative 8 or negative x to the 8th power, and then if I have the square root of a coefficient, but the x is not in that square root, it's just x to the 3rd power and x, or just a constant number here, those are all polynomials. Over here would be examples of things that are not polynomial functions. Having a square root, or having a power that's a fraction, having a negative power, or having a variable in the denominator. Those are all examples of things that are not polynomials. Some characteristics of polynomial functions are that they have smooth curves, meaning there's no sharp corners like in an absolute value function or anything like that. And they are continuous, meaning we can draw it without lifting up our pencil or a pen. So there's no breaks, no jumps, no holes, nothing like that. We can talk about the end behavior of a polynomial, and what we mean by end behavior is what happens as x goes to infinity and negative infinity. So what happens at the ends of our function. And if the degree is even, meaning that largest exponent is even, then the arrows are going to be going in the same direction. If they're even and the leading coefficient is positive, meaning the number out front is positive, then those ending arrows are both going to be going up, meaning it rises to the left and rises to the right. Or as x goes to negative infinity and positive infinity, y goes to infinity. If the leading coefficient is negative and the degree is even, then those ending arrows go down. If the degree is odd, then those ending arrows are going to be going in opposite directions. So with the degree being even, the ending arrows are going in the same direction, either both up or both down. If the degree is odd, then the ending arrows are going in opposite directions. If the leading coefficient is positive, it has a positive slope like this. If the leading coefficient is negative, it has a negative slope like this. Again, falls to the left, rises to the right, rises to the left, falls to the right. So we're going to do a couple examples of this topic here. And it says, use the leading coefficient test to determine the end behavior of the following functions. So in the using what we were just talking about here, that test to determine the end of behavior, I don't need to multiply out this whole thing because that would be a lot of work. I'd have to multiply x plus 5 4 times, and then 2x minus 7 6 times, and then times 3x. That would be a lot. But what we can do is just figure out what would the largest term be. So if I want to know what the largest term is, if I multiply this out 4 times, the largest term from that would be x to the 4th power. And then out front we have a 3x. And then from this term, if I had this raised to the 6th power, 2 to the 6th power is going to be 64. And then x to the 6th power would just be x to the 6th power. Well, if I multiply all of that out, x times x to the 4th times x to the 6th is going to be x to the 11th. So that's an odd degree. So that means it's one of these two cases. And 3 times 64 is 192. And that's positive. So that means it's this scenario here, where my ending arrows are going up this way and down this way. So it rises to the right and falls to the left. Okay. The next one, we have negative 4x cubed. And from here, x minus 1 squared, the largest term would be x squared. From here, this isn't raised to anything, it would just be x. So x cubed, x squared, and x gives me negative 4x to the 6th power. That is an even degree, so it's going to be one of these two scenarios. And the leading coefficient is negative, so that means both ending arrows are going down. So the way we could write that in words would be it falls to the left and right. All right, moving on to the next page here. We're going to be looking at some other information about polynomials. And here we have zeros of polynomials. So we talked about this in the last video, but another term for zeros of polynomials would be roots, solutions, or x-intercepts. And this is where the function is equal to 0, where it crosses the x-axis. We can also have multiplicity of roots, and what this means is we could have multiple copies of them, like what we just saw where we have a factor raised to a power. That would be the multiplicity of that root. Well, if r is a certain root of a polynomial and it has an even multiplicity, then the graph touches the x-axis and turns around at that value. If it has an odd multiplicity, meaning like there's an odd number of copies of that root, then the graph crosses the x-axis at that value. So in these next two examples, it says, find the zeros of f of x, give the multiplicity of each zero, and state whether the graph crosses the x-axis or touches and turns around. So what we're going to do, I didn't leave very much space right here, but for number, let me rewrite it over here real quick actually. 2, we'll have f of x and I'll go ahead and just wipe this out. So creating some space there for both of those problems. For this first one, we don't have any x's out front. We just have x equals -1 and x equals 3 halves. So those are my two x values. This one doesn't have a exponent here, so the multiplicity is 1, meaning I only have one copy of that root. But here it's being squared, so the multiplicity is 2. Again, if the multiplicity is odd, that means it crosses the x-axis. And if the multiplicity is even, it touches and turns around. Now, what we're trying to do in finding these pieces of information is get clues about what the graph looks like, because you're going to be needing to graph polynomials by hand without or in trying to figure out what the graph looks like. And that's a little bit harder to do than what we were looking at in the last video, where you just have a formula and all of the graphs pretty much look the same, just maybe flipped over or stretched or whatever. Polynomials have a lot more variation in what they can look like. So when we're looking at the end behavior, when we're looking at the multiplicity of roots, all of those things are to give us clues about what the graph looks like. In the next example, we have f of x equals -3x, so that gives me a root of 0. 4 minus x, that gives me x equals 4. And then x plus 2 gives me x equals -2. And then we can go ahead and state their multiplicity. There's only one copy of 0, so the multiplicity is 1. And both of these have a multiplicity of 2. Again, if you have an odd multiplicity, what that means is it crosses the x-axis. If you have an even multiplicity, that means it touches and turns around. The next thing we're going to look at is the intermediate value theorem, and what this tells us is where there are zeros or roots or x-intercepts. And basically what the intermediate value theorem says is if I have an x value here where at that x value the function is negative, And then if I have another x value over here and the function is positive there, because this is a polynomial function, there's no jumps or gaps or holes or anything like that. If I have a value below the x-axis and then a value above the x-axis, between those x values, somewhere it's going to have to cross the x-axis, meaning we'll have a root there. That means there will be some spot where the graph actually touches the x-axis. And we know that if it's negative here and positive here, it's not like the function can go around the x-axis. It's going to have to cross it at some point between a and b. So what we can look at then with the intermediate value theorem is finding zeros. So we know that this is a polynomial here. We want to show that the polynomial has a real solution or a real x-intercept, a real zero, a real root, all meaning the same thing there, between 2 and 3. So these are both x values. This is x1 and x2. So I want to find f of 2 and I want to find f of 3. And if one of those gives me a positive value and one of those gives me a negative value, then that means that we have a 0 between 2 and 3. So plugging into 2 cubed is 8, minus 2 times 2 would be 4, minus 5. 8 minus 4 minus 5 is negative 1. So we got a negative value. Plugging in 3 cubed is 27. 2 times 3 is 6, and then minus 5. And 27 minus 6 minus 5 is 16. So we have a negative value and a positive value, therefore, and these 3 little dots here mean therefore, there is a root between 2 and 3. Okay. Now the next thing we're going to talk about is turning points, and a turning point is a value or a location on the graph where it turns around, where the graph turns from increasing to decreasing or decreasing to increasing. So if I have a graph that looks something like this, this would be a turning point here. This is a turning point, and this is a turning point. It goes from decreasing to increasing, and here it goes from increasing to decreasing. So the number of turning points that a polynomial can have is at most n minus 1. So if the degree is 4, it can have at most 3 turning points. Okay, so it doesn't mean it definitely has 3. It just means it can't have more than 3. That's the maximum number of turning points that it could have. So now that we've gone over all these pieces of information, what we're going to do now is go over how to graph polynomials. So when we're graphing polynomials, we have a lot of different things we can consider, and this list here is really just a list of all the different things we could use to help us figure out what the graph looks like. So first, we could use the leading coefficient test to determine the end behavior, seeing what's happening at the very end of the graph. The next thing we could do is find x-intercepts or y-intercepts to give us some points for the graph. We can also determine the roots and use that multiplicity of the roots to determine if at a root it touches the x-axis and turns around, or if it crosses the x-axis at that value. We can use symmetry. We can look at what we learned previously about even and odd functions. And we can also find the number of turning points that the graph can have. So all of these pieces together can help us get an idea of what the graph looks like. So looking at our first example here, we have f of x equals x to the 4th power minus 2x squared plus 1. The first thing I'm going to do is look at my end behavior. Well, the degree of this polynomial is 4. That's an even number. So either both my ending arrows are going up or they're both going down. Because the leading coefficient is positive, that means both ending arrows are going up. The next thing I want to do is look at finding some easy pieces of information. Usually, finding our y-intercept is pretty easy. We're just plugging in 0 for x. And if I plug in 0 for x everywhere, 0, 0, and 1. So I know I have the point 0, 1. Now, I can also factor this polynomial, and though this is not a quadratic equation, it does follow a quadratic pattern. We have degree 4, then degree 2, then a constant. So if this degree is half of this degree, and then you have a constant on the end, it's just 3 terms, that's a quadratic pattern. So if I used the x method here, I would have 1 on top and negative 2 on bottom. Negative 1 and negative 1 multiply to 1 and add to negative 2. So instead of it being x minus 1 and x minus 1, it's actually going to be x squared minus 1 and x squared minus 1. So from there, I can go ahead and factor both of those because these are both difference of perfect squares. So that would be x plus 1, x minus 1, and then this would be the same thing, x plus 1 and x minus 1. And this is where all the different factoring skills we've learned so far, everything from Unit 1, is really important because I need to know factoring by grouping. I need to know how to use the X method. I need to know the quadratic formula. I need to know factoring with a quadratic pattern. All of these different tools might pop up randomly anywhere, really for the rest of your math career. So I have 2 copies of x plus 1, so I can go ahead and rewrite this as x plus 1 squared. And then I have 2 copies of x minus 1. So this is equal to this. That means I have a root of x equals negative 1 and x equals positive 1. And the multiplicity of both of those are 2, which means it touches and turns around. Okay. Now this is a degree 4, so the other thing I can look at is how many turning points I have, and I have at most 3 turning points. So all of these pieces can kind of give us some clues. Let's see what we have so far. We know we have the point 0, 1, so 0, 1. We know our ending arrows are going up. We know we have roots at negative 1 and at positive 1. And we know we have at most 3 turning points. So let's just see what we have so far. We know that at these x-intercepts here, that my graph is going to touch and turn around. It's going to touch and turn around. So if I have 3 turning points, if I'm coming from here and I touch and turn around, that's 1 turning point. We know it has to go through this point, so it has to curve this way to get to this point. And then it has to be coming back over this way. So we have 1 turning point, another turning point, and another turning point. That's 3 turning points. There's no other curves or turns or anything here. There's the graph of our function. And if you typed this function into your graphing calculator, this is about what it will look like. So there's our graph. We're going to do one more. And in this example, we have 4 terms now. Again, starting with our end behavior, my largest exponent is 3, which is odd. So that means my ending arrows are going in the opposite order. But my leading coefficient is negative, so I'm going to have like a negative slope look here. So it'll go something like this. Okay. I won't go ahead and draw them on my graph quite yet. Again, an easy starting piece is to find our y-intercept, so I can go ahead and plug in 0 for x, excuse me, and find my y value. If x is 0, that's 0, 0, 0, and negative 12, so that's my y-intercept. We know we have at most 2 turning points because my degree is 3, so 2 turning points at most. Doesn't mean we have to have 2, it just means that we can't have more than that. And the fact that this is 4 terms makes me think we might want to use factoring by grouping. So I'm going to go ahead and use factoring by grouping here. I'm going to go ahead and pull out a negative x squared. And the reason I'm pulling out a negative is because I notice here the negative is in between the terms. So I'm going to go ahead and pull it out from this one. And then I'm left with x minus 3, not x plus 3. And then factoring by grouping here, 4x minus 12, I'm going to go ahead and pull out a 4. And I have x minus 3. So common factor of x minus 3. And then I have negative x squared plus 4. And then I have x minus 3. And you could pull out a negative from this if you wanted to. I'm going to go ahead and pull out a negative, and then I'm left with x squared minus 4. Just pulls a negative out there. And that negative 1 I'm going to go ahead and just put out front. And then I have x plus 2 and x minus 2. So those gives me all my x-intercepts. X equals 3, x equals negative 2, and x equals 2. So it touches at negative 2, it touches at 2, and it touches at 3. We also know we have a y-intercept of negative 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And we know our ending arrows are going something like this. And we know we only have 2 turning points. So if I'm thinking through in my head, okay, how could this go here? I'm thinking, all right, so if we're starting here and we go through, we know that our graph is going to go through all of these points because they all have a multiplicity of 1, which means that it actually crosses the x-axis. It doesn't touch and turn around like the last example. It's not bouncing off that point. It's actually going through. Okay. So if I think about my graph here coming through this point and coming all the way down, and it's going to go through this point, but it's going to have to come back up to go through here, and then it's going to have to go through here as well. That gives me 2 turning points, and that gives me the shape of my graph. Now, I don't know that this is the lowest point here. It could be somewhere else. It could be over here, or it could be over here. But when you're graphing these by hand, these are the pieces of information I'm looking for. I'm looking for a y-intercept. I'm looking for where it crosses the x-axis, the end behavior, and this is a good enough sketch of your graph. Now we could make a table, we could plug in some more points, we could plug in -1 and 1, we could plug in something in between here, but I'm not going to ask you guys to do that. This is going to give me a good enough sketch of your graph that it goes up, goes through, goes through, goes through, comes down here, and gives me that shape of that graph. And that is going to be it for this video for us. So that's the end of part 2.